In the previous series, we introduced the basic principles of quantum mechanics, the theory that describes atoms and molecules. Thermodynamics, by contrast, describes matter on a microscopic scale. Remarkably, it was developed before quantum mechanics, at a time when even the existence of atoms was still debated. Yet, guided by the principles of thermodynamics, engineers were already able to design increasingly efficient steam engines. To study a physical system, we first need a way to describe its state. In quantum mechanics, the state is represented by a state vector psi. In thermodynamics, an equilibrium state is characterized by microscopic variables related through an equation of state. Fortunately, we're already familiar with one important example, the ideal gas law PV equals to nRT, where P is the pressure, V is the volume, N is the amount of gas in moles, E is the absolute temperature in Kelvin, and R equals to 8.314 joule per Kelvin per mole, which is the ideal gas constant. If the amount of gas is fixed, only two of the three variables, P, V, T, can be chosen independently. For example, once V and T are specified, the pressure is determined by the ideal gas law. Thus, the equilibrium state of this simple system can be specified by just two variables, such as V and T. The description is remarkably compact. It is far simpler than specifying the infinitely many quantum amplitudes that may be required to describe a quantum state, or tracking the positions and momenta of every atom in the gas. We now introduce two important concepts: the system and the surroundings. The system is a part of the universe we chose to study, while everything else is the surroundings. Consider a solution in a test tube. An open test tube is an open system, able to exchange both matter and energy with its surroundings. Once sealed, it becomes a closed system. It can still exchange energy, but not matter, because the test tube is rigid. Its volume is approximately constant, so pressure-volume work is negligible. To allow such work, we instead need a movable boundary, such as a piston. A sealed and perfectly insulated system is isolated. It exchanges neither matter nor energy with its surroundings. Energy crosses the boundary as either heat, Q, or work, W. Heat is the energy transferred down a temperature gradient, while work is force times distance. We take energy transferred into the system as positive. Thus, Q greater than 0 when the system absorbs heat, and the W is greater than 0 when work is done on it. Heat and work are not energy stored in the system. There are two ways of transferring energy to the system. What we have described is essentially the first law of thermodynamics, which is written as delta U equals to Q plus W. It states that the internal energy U of a system can change through either heat or work. Once energy enters the system, it does not retain a label indicating how it arrived, just as a purchase may be made with cash or a credit card, but the money has the same value either way. Notice that we write delta U but not delta Q or delta W. Internal energy is stored in the system, so it makes sense to speak of a change in U. Heat and work, however, are not stored. They describe energy being transferred across the system boundary. Therefore, we write Q and W rather than change in heat or work. It follows directly that for an isolated system, there's no heat transfer to or work done on the system, so energy of an isolated system is constant. We now consider some important properties of the internal energy U. First, U is a state function, or a function of state. Its value depends only on the state of a system. For a system with a fixed amount of matter, we may write, for example, U as a function of V and T. Each state V and T can be represented as a point in a two-dimensional state space, and U assigns a value to every point. The change in internal energy between an initial state V1 T1 and the final state V2 T2 is written as delta U as an integral from v1 t1 to v2 t2 du, which is u of v2 t2 minus u of v1 t1. Because u is a state function, delta u depends only on the initial and final state, not the path taken between them. Importantly, the change in the state function is path independent. For example, we may first heat a gas, then compress it, or first compress it, then heat it. Provided that the initial and final states are the same, the change in internal energy is also the same. Thus, the integral of du is independent of the path between the two states. It follows immediately that the integral over du equals to 0, where the circle on the integral sign indicates the integration around a closed path. After returning to the initial state, the internal energy must return to its initial value. The quantity du is therefore called an exact differential. Since u equals to u of v and t, it can be written as du equals to partial u partial v at constant t times dv plus partial u partial t at constant v times dt. A third equivalent property is the symmetry of the mixed second derivative, partial to u over partial v partial t equals to partial to u partial t partial v. The equivalence follows from Green's theorem, the two-dimensional form of Stokes' theorem. We will not explore the mathematical details here. Heat and work are not state functions. Their value depend on the path taken between two states. They are therefore called path functions, and their inexact differentials are denoted by d bar q and d bar w. The differential form of the first law is du equals to d bar q plus d bar w. This is the most useful form of the first law. Since du is exact, we immediately have the integral for a closed path of d bar q plus d bar w equals to 0. Thus, although heat and work are individually path dependent, their sum give the change in the state function u, which is path independent. We now consider expansion work. Suppose a gas is confined in a cylinder by a movable piston of area A. If the gas expands and moves the piston by a small distance dz against an external pressure Px, the work done on the gas is d bar w equals to minus f dz equals to minus px a dz equals to minus px dv, where F is the force exerted on the piston and dV is the small change in the volume of the gas. The negative sign reflects our convention that work done on the system is positive. During the expansion, the gas does work on the surroundings, so W is less than 0. If the external pressure is constant, then W is minus the integral from V1 to V2 Px dV equals to minus Px into V2 minus V1 equals to minus Px delta V, the change in volume. For free expansion into a vacuum, the external pressure is 0, and hence W equals to 0. In a reversible expansion, the gas pressure exceeds the external pressure by only an infinitesimal amount, so in the reversible limit, the external pressure goes to P, so we have W reversible equals to integral from V1 to V2 P dV. The condition P equals to Px is called mechanical equilibrium. Reversible expansion proceeds through states infinitesimally close to this condition. Therefore, we have W reversible equals to minus the integral from V1 to V2 P dV equals to minus the integral from V1 to V2 nRT over V times dV, which is minus nRT log V2 over V1. An ideal gas has an internal energy that depends only on temperature. Thus, for any isothermal, i.e. constant temperature process, delta U equals to 0. And the first law gives Q equals to minus W. For an irreversible expansion through a constant external pressure and a reversible expansion between the same states, respectively, Q irreversible equals to Px delta V and Q reversible equals to nRT log V2 over V1. The two paths have the same initial and final states, but different values of Q and W, confirming that heat and work are path dependent. A Mon expansion path connecting the same states. The reversible path produces the maximum work. With our sign convention, W reversible is the most negative. For an isothermal ideal gas expansion, the heat absorbed by the gas equals to the work it does on the surroundings, while its internal energy remains unchanged. Clearly, at constant volume, no work is done, so we have du equals to d bar qv, or equivalently, for non-infinitesimal change, delta U equals to qv. A natural question this raises is that whether there is a state function that is the same as heat added at constant pressure. To answer this, consider enthalpy, which is defined as H equals to U plus PV. Then take the differential on both sides, so we have what's on the screen, and eventually equals to d bar qp. Thus enthalpy is heat added to the system at constant pressure, and enthalpy is also a state function, since internal energy, pressure and volume are all state functions. So I have the integral on a closed path dH equals to 0. We now turn to the experimental measurements of internal energy and enthalpy. In quantum mechanics, the solutions of the time-independent Schrödinger equation are energy levels, which are tested using spectroscopy. Photons are absorbed or emitted when their frequencies match the energy gaps between the quantum states. The corresponding experimental technique in thermodynamics is calorimetry, which determines heat transfer from the resulting change in temperature. The central experimental quantity is the heat capacity, which relates the heat transferred to the temperature change. There are two types of heat capacities: constant volume heat capacity CV and constant pressure heat capacity CP, defined as follows. For a small temperature interval over which the heat capacity is approximately constant, we have delta T approximately equals to QV over CV at constant volume, and delta T approximately equals to QP over CP at constant pressure. Thus, a substance with large heat capacity requires a large amount of heat to produce a small temperature increase, whereas a substance with a small heat capacity changes temperature more readily. In general, heat capacity depends on temperature. At constant volume, we have U of T2 and V minus U of T1 and V equals to the integral from T1 to T2 Cv of T dt. Or equivalently, we can put U of T1 and V on the other side. And similarly, we have an analogous expression at constant pressure for enthalpy change. Therefore, if the internal energy or enthalpy is known at a reference temperature, calorimetric measurements of Cv of T or Cp of T allows us to determine its value at any other temperatures. We have already considered an isothermal process, which occurs at a constant temperature. We now turn to another important type of process, an adiabatic process, in which no heat is exchanged between the system and its surroundings. Consider a reversible adiabatic process involving 1 mole of monoatomic ideal gas, taken from an initial state V1 T1 to a final state V2 T2. Its constant volume heat capacity is Cv equals to 3 over 2 R. Because the process is adiabatic, dq equals to 0, and for reversible process, P external goes to P. So the first law gives du equals to dw equals to minus P dV equals to minus RT over V dV, where we have used the ideal gas equation for 1 mole. The internal energy of an ideal gas depends only on temperature, so du equals to Cv dt. Equating the two expressions for du gives Cv dt equals to minus RT over V dV. Using Cv equals to 3R over 2 and rearranging gives 3 over 2 into dt over t equals to minus dv over v. Integrating between the initial and final states gives 3 over 2 log t2 over t1 equals to minus log v2 over v1, and the final rearrangement gives the equation on the screen. So this relation allows any one of v1, t1, v2, t2 to be determined from the other three. During an isothermal expansion, the gas absorbs heat and converts it into work, while its internal energy remains unchanged. During an adiabatic expansion, no heat enters the gas. It must therefore do work at the expense of its own internal energy, causing its temperature to decrease. In this chapter, we introduced the first law of thermodynamics, together with several basic thermodynamics concepts and processes. The first law imposes a fundamental constraint. Any physically possible process must conserve energy. However, energy conservation alone does not tell us whether a process will actually occur or in which direction it will proceed. In the next chapter, we'll introduce the second law of thermodynamics. The second law determines the directions of spontaneous change and places fundamental limits on the efficiency of heat engines, questions that plays a central role in the development of thermodynamics during the Industrial Revolution. See you then. Thank you for watching.